Hey everybody, welcome back to another episode of Physics with Dr. T. I'm Dr. T, your host, and this week we're going to be taking a look at the walkthrough for polarization of light, where we're going to be looking at the wave nature of light. This is one of those characteristics that cannot be described through the particle nature. But before we get into all the physics of that, let's talk about this week's PreLab activity. In today's PreLab, the main goal here is to demonstrate that light has transverse waves as opposed to longitudinal waves. The only way we can demonstrate that is to be able to get familiar with what the difference between transverse and longitudinal waves are. So for a transverse wave, it's going to oscillate on a medium that is perpendicular to the direction of motion, whereas a longitudinal wave goes along the direction of motion. Now if we set this full far apart, we can see that the longitudinal waves are able to pass through this no problem. And even if I made this smaller for a smaller slinky, it should still do the same job. This is why sound is able to pass through doors. But when we have a wave with an amplitude that's larger than the gap, we can demonstrate that the transverse wave can pass through this gap, a transverse wave where the amplitude is parallel with the gap direction. And we can see that that pulse goes through. By comparison, a big pulse is muted significantly and does not pass through the gap. So you will demonstrate this with your own wire, with your own cable, cord, yarn, rope, on your own gap, maybe a door, maybe a collection of books that are next to each other, and just try a few things and see if you can confirm that the wave passes through more easily when it's aligned with it and less easily when it's perpendicular to the gap. In your studies of waves, you should have found out by now that there's two types of waves. There's transverse waves and longitudinal waves. Longitudinal waves are those where the wave propagates along the same direction that the medium changes position, whereas transverse waves are the ones that the medium changes position perpendicular to the direction of the wave motion. Not my finest hour. If we're right in this lab that light is transverse, then we'll see that there's a random orientation of the light, different orientations, where we'll talk about the amplitude of the light. Down the way we'll find out that that's the electric field intensity, but for now we're just going to talk about the amplitude and the intensity, the amount of light that's come to us. And this is all randomly coming to us, and so there's different intensities going around different angles. And N represents the direction of the wave propagation. As you'll see when you start looking at the equipment set up here momentarily, you'll find that there is an angle between two polarizers that will be of importance, and how much light actually transfers through the polarizer filters that you'll be working with. And the relationship that is used is this one is called Malus Law, where it shows that the intensity of the light after it's passed through the second filter is equal to the intensity between the first filter and the second filter, and a cosine squared of the angle between those two filters. So each filter will be measured at some angle we'll call phi, and that's just another Greek letter. There's 24 of them, I think it was. Anyways, the angle for each of these relative to some fixed position, which is probably going to be the workbench, the optics bench that you're working with, we're going to call that phi, and then the angle theta we're going to refer to as the difference between those reference angles, phi2 minus phi1. Now go on this here, and this is referred to as Malus Law. You will demonstrate Malus Law in the course of your experiment, and you will make sure that you can actually see that cosine squared behavior, and then you'll map the intensity as it comes out of the second filter as a function of the angle that you measure. If it turns out to be true, then that will mean that the light passing through the first filter will have been reduced only to the light that's passing through with an alignment along the axis of that filter. And then we'll use the second filter to demonstrate that that light was in fact aligned a certain way, because by tilting it different ways, you will influence the intensity. This should convince you then that the wave displacement of a photon of light is perpendicular to the direction of its motion. And as a result, we can say that light is transverse. Make sure that you include that in your report. Light is transverse and not longitudinal. For the second part of your experiment, you're going to want to be finding Brewster's angle. Now, this actually may go a little bit more to the heart of polarization in general, because it will demonstrate not only that light is randomly polarized initially, but also can demonstrate that there are two different orientations, and that transfer between the surface will highlight that significantly. If you reflect back on what you did last week, light incident on a surface will have a reflection and a refraction. Both will take place in varying intensities. You have your incident angle and your reflected angle are going to be the same as it was before. Your refracted angle corresponds to Snell's law. No surprise there. Now let's talk in terms of polarization. For the incident light, we assume for the moment that it's randomly polarized. When it reflects and refracts, you will have some mixture of polarization, but both of these will be more polarized than they were before. Brewster's angle corresponds to an angle of incidence where the incident beam, randomly polarized, is split completely into purely polarized beams for the reflected and refracted. This means that you will work with a group that's neighboring to you to set up your equipment in order to demonstrate that you have zero reflection on one and 100% transmission through the other. The way to tell that you've reached Brewster's angle condition is that your reflection angle and your refraction angle are 90 degrees now to each other, and that you have full polarization in one direction, you have full polarization in one direction, and then full polarization in the 90-degree angle from there. A little bit of movie magic, and so the index of refraction is, in this case, doesn't have any subscripts. Well, when you assume that air is going to be about 1 for the index of refraction, then the material is going to be the index of refraction of the material. You should be working with acrylic, so you should get a Brewster's angle that corresponds to that index of refraction. Check it, see if it works. Do a percent error, do a percent error, do a percent difference calculation to confirm that you have measured the right angle. And that pretty much does it for the theory. To perform this lab activity, you're going to need a light source, which is going to come in the form of a red or green laser. If your laser is a little too weak, let us know. We'll replace the batteries to give it the best boost you can work with. You will have an optics mounting stand and 2 polarizing filters. Now, they have a degree angle measurement on the outside edge, and you can adjust them simply by turning them in the mounts. Now, you place these gently into the mount like so. Make sure that you do not touch the polarizing filter surfaces. You don't want to cause any damage there. But you can rotate these fairly freely, and you can use this pin as a reference point as your measurement. Now, you will be on a bench, and there will be a laser passing through here, so make sure you're very careful not to get in the path of the laser for your eye. You do not want to get any eye damage to that. But you should be able to look up and make adjustments to your filters from there. At the other end of your laser beam pathway is going to be a Pasco light sensor. The Pasco light sensor has a sensitive input right here that you want to align your laser pointing into. It's got another end that has some of these pins that you connect through this BNC connector and mount into your 850 interface. You'll be given a mount that you can adjust the height of the clamp, and while doing so, adjust the height of your laser. You just simply set that in there and adjust it as necessary. Try and make sure it lays as flat as possible, fits in that nook very nicely, and then turn it on and off as necessary. For your Brewster's angle measurement, you will have this rotating platform which is seated, has 4 little pads that you place onto the optical track, and then you can adjust the top gently. You notice that the pins are not moving down below, so you can adjust this more freely. And you place your optical instrument on top of this and rotate it around. Make sure that it's aligned with your laser. You have your normal measurement here, you have your component surface, and you have your degrees measurement all around. If you're struggling to get your alignment squared away with a laser, it might be helpful to use one of the light sources nearby. You can set it on one of the slots so that it projects on here and you can follow the pathway better as you're trying to get your Brewster angle. Or you can adjust your, you can use the solid light source here and use that to help you align. When you come in, your equipment is going to be close to set up, but it's not going to be fully set up for you. You will need to do a little bit of assembly and alignment yourself. So the best way to do that is to make sure you put your polarizer mounts into the Outtakes track bench. You can take these polarizing filters out gently so that you have a clear pathway while you align your laser with the sensor, which is not on here. It's going to be on a clamp at the edge of your bench. Try to make sure that your laser beam is aligned with this center of the bottom track. That way you have a nice clean beam path, and you can set up another piece of paper down at the end or something to make sure that the beam continues in a straight line along the track. But the important part is that you have good alignment, and that goes basically through the center of your optics mount. Once you have all your optics aligned, you want to do some tests with the Pasco software to check the intensity, because this light may be too intense for the actual sensor to pick up, and so it will saturate right around 97%. So what you want to do is add your filter in place, and the first thing you want to test to see is the light coming out of your laser source already polarized. You'll explore that by adjusting this and seeing if there's any dips in your intensity. If there are any dips in there, then you know that your laser is polarized, or at least partially polarized. If there's not any dips, then you're free to work with this as well as you can. Check the intensity drop off between no filter and with filter to see if it does meet the 50% expectation. And then once you've done that, you can add your second filter and begin your experiment. To do your experiment, what you want to do is rotate this through the range of percent differences at kind of a steady rate, and show that the relationship between the lasers are 50%. Show that once you're ready to take data, what you want to do is begin rotating. You have your first one fixed to give you your maximum. If your laser is in fact polarized, if it turns out that your laser is polarized, you'll want to adjust your first filter so that you have the maximum output that still can be measured and adjusted in Pasco. Anything that's, if it stays above 97%, then it probably is oversaturated and you're too bright, so you got to dial it down just a bit. Try and get between 75 and 90 if you can as your maximum. As soon as you put your light polarizer in here and you confirm Malus Law, you start rotating the polarizers steadily through the range of angles. Go around 2 or 3 times to make sure that you're definitely seeing a cosine squared relationship. Once you've done that, then it's a matter of going to about every 5 to 10 decimal. Then it's a matter of going to about every 5 to 10 degrees rotation for this. You'll record this into the table that's available to you, or you can create in your own Excel spreadsheet. And you'll observe the measurement. You'll make a measurement, and then simply click on the data representing, once you've got a fixed value, of what the intensity of that laser beam is as at that angle. You continue that all the way around, go all the way around full 360 degrees to confirm that you have measured every angle. And then you'll use that data to construct a plot for your lab report. Okay, so now that you have an idea about what's going to happen in the lab, let's talk briefly about the lab reports. These lab reports are going to be a short lab report, so you will be writing the main sections and you will be presenting your data in a more formalized manner. It should only take about 3 or 4 pages at the most. You'll want to make sure that you include with your data the angle between the polarizers and the intensity as a function of that angle. You also want to make sure that you export the data that has to do from the Brewsters angle so that you can demonstrate that you were able to show different polarity. Make sure you record the angles from a consistent reference angle. It might be useful to take pictures throughout the course of the experiment just to make sure that you have some good feedback or fallback to go to. Polarization also shows up in a lot of medical applications, so it might be worthwhile for those of you who are in kinesiology and other areas of interest in medicine to take a look at what's out there in the literature, or maybe talk to somebody who's in your department that knows a little bit about various therapies, and see if you can incorporate a little bit of comment about that in your lab report. But you want to definitely focus on the fact that you were able to demonstrate in the lab that light is transverse, that you were able to demonstrate it's not just transverse, but that it can be polarized transverse, and that the way that it reflects and refracts off of surfaces is another example of the wave nature of light. Well, that does it for this week's walkthrough. If you have any other questions, make sure you ask me, make sure you ask your TA, or again, you can consult your peers. Peer learning is a very important factor of the learning experience. And until next time, we'll see you in the lab. Bye then.